espaçonauta! Vamos falar sobre o 3 e Atlas e as revelações da NASA sobre esse misterioso cometa interestelar. Seguinte, pessoal, a NASA realizou uma coletiva de imprensa onde apresentou vários dados aí e detalhes muito importantes sobre o cometa interestelar 3 e Atlas. É isso mesmo, ele é um cometa. Se você não sabia, ele é um cometa. Essa coletiva foi realizada aí no último dia 19, né? 19 de novembro, a gente tem nem uma semana dela. E nessa coletiva aí, a NASA apresentou também as imagens captadas pela sonda orbital de Marte, a MRO, ou MRO, que possui entre as sondas orbitadoras ali, a melhor câmera fotográfica. A HiRISE, que é a câmera mais incrível desenvolvida ali para fotografar o solo marciano, é de fato a melhor dentre todas as outras dos orbitadores que estão ali em Marte. Ela foi concebida para fazer imagens de alta definição do solo marciano, com uma iluminação ideal, devido ali ao brilho do Sol no planeta. E a uma altitude máxima ou a uma distância máxima de 400 quilômetros do solo do planeta Marte. Ela não é, gente, uma câmera para fazer imagens de um objeto extremamente difuso e com muito pouco brilho na escuridão do espaço a 30 milhões de quilômetros. No caso aí, eu estou falando do cometa interestelar 3 e Atlas, quando da sua máxima aproximação a Marte. Mesmo assim, os pesquisadores ali da missão da HiRISE aceitaram esse desafio e conseguiram a melhor imagem da aproximação do 3 e Atlas com o planeta Marte. Claro, né, gente? Nem de longe é a melhor imagem obtida desse intrigante visitante alienígena. Mas também nunca pretendeu ser a melhor. Ao contrário dos anúncios sensacionalistas aí que polvilharam a internet de outubro para cá, né? Principalmente depois do shutdown da NASA ali, que foi uma paralisação devido à falta de verba aí. E aí a galera começou a falar que a NASA estava escondendo o que seria a melhor imagem do 3 e Atlas e que poderia esclarecer todos os mistérios. Mentira. A gente já sabia disso, né? A gente já sabia que essas imagens dos orbitadores de Marte aí, e era o que a gente tinha para pegar essa aproximação, até porque Marte está em oposição com a Terra nesse momento, que é do outro lado, e a gente não consegue enxergar do outro lado do Sol, né? Então a gente já sabia. Eu vi, por exemplo, eu sempre dei uns toques sobre isso aqui no canal, vi um vídeo do Felipe Haim dedicado a isso. Se você está achando que é mentira minha, pode ir lá no canal do Haim e que você vai ver ele explicando exatamente, falando para a galera não esperar muita coisa, que essas câmeras eram muito limitadas, enfim, né? Só que é o seguinte, para mim, o mais importante dessa coletiva da NASA não é a imagem captada com esse esforço descomunal aí que os pesquisadores, os cientistas da MRO e sua câmera HiRISE conseguiram, mas sim o compilado de dados e análises que os cientistas da NASA trouxeram sobre a natureza de um dos cometas mais intrigantes que nós já tivemos a oportunidade de observar. O quarto objeto interestelar a adentrar o nosso sistema solar e o terceiro que vai passar direto por ele. Você estava achando que era 3, né? Pois é o que eu falo com vocês. Aqui a informação é kit. Nós tivemos 4 objetos interestelares descobertos. Só que um deles, ao contrário dos outros 3, não passou pelo sistema solar. Ele caiu na Terra. Caiu lá perto de Papua Nova Guiné. E foi designado meteorito interestelar, ou IM1. Tá certo? Inclusive, o rei da pataquada lá, o Dr. Avi Loeb, na época, fez uma expedição para tentar encontrar restos desse corpo lá no mar da Papua Nova Guiné. Tá? Então, daí vocês veem. Por que falam 3? Porque são 3 que estão passando pelo sistema solar. O Oumuamua, entrou no sistema solar e saiu, o 2i Borisov entrou no sistema solar e saiu, e o 3i Atlas, que entrou no sistema solar, provavelmente vai sair também, a menos que eles tenham uma colisão futura aí com um corpo tipo Júpiter, uma lua de Júpiter, uma coisa assim que é improvável pela órbita dele. Tá certo? Bom, então é por isso tudo aí que eu estou falando que eu quis trazer para vocês na íntegra a coletiva de imprensa da NASA em português. Um trabalho de colaboração do nosso amigo Alfredo Lopes Moraes, lá de Portugal, que traduziu esse material e legendou de maneira brilhante. O material ficou incrível, galera. Assisti ontem, assim, dá gosto de ver, né? E eu já vou aproveitar que eu falei aqui do Alfredo e mandar aqui, viu, Alfredo? Meus sinceros agradecimentos aí, um grande abraço para você, Alfredo. Muito obrigado mais uma vez, né? E pedir para que vocês também mandem aí um salve para o Alfredo aqui nos comentários. Já vai lá nos comentários e já manda um grande salve para o Alfredo para você não esquecer, né? E agora eu vou fazer para vocês um convite a vocês, espaçonauta, para que se dê a chance de aprender muita coisa sobre esse intrigante cometa interestelar, o 3i Atlas, assistindo a esse vídeo aí da coletiva de imprensa da NASA até o final. A galera que é espaçonauta já me acompanha, já sabe que não é cometa, já sabe que é um cometa, né? Olha eu caçando tumulto aqui. Já sabe que é de fato um cometa, né? Mas se você que tem aqui, você acompanha aí os canais mais sensacionalistas e não acha tanto que é cometa e tal, eu vou te pedir o seguinte, abre sua mente e presta atenção nesse material de conteúdo científico ímpar, tá? Assiste ele até o final aí, que ele pode te ajudar a entender muita coisa sobre esse objeto e pode te ajudar a entender também como que a ciência trabalha. Bom, beleza, galera, já conversei demais, vamos embora pro vídeo que eu tô doido para ver de novo. Vamos embora, vamos lá.
Good afternoon and welcome to NASA's Goddard Space Flight Center. We are live today with NASA experts who are excited to share the latest images we have of the interstellar comet 3I Atlas. 3I means third interstellar, and Atlas refers to the NASA-funded Atlas Survey telescope, which made the discovery. We are joined today by Amit Kshatriya, NASA's Associate Administrator, Nikki Fox, Associate Administrator for NASA's Science Mission Directorate, Sean Domagal-Goldman, Director for the Astrophysics Division, and Tom Statler, Lead Scientist for Solar System Small Bodies in the Planetary Science Division. We'll be taking questions from the media on the phone bridge and through social media, but before we get started, let's learn more about this fascinating comet and share some images. Amit, kick us off.
Hi everyone, America leads the way in space exploration. As Courtney noted, a NASA-funded telescope, the Atlas Survey Telescope in Chile, first reported observations of the comet on July 1st, 2025 to the Minor Planet Center. And NASA has been tracking and studying Comet 3I Atlas ever since. We're here today to give you the latest of what we know about Comet 3I Atlas and what we still want to know. But first, what is a comet? It's a small, natural, solid body that is a combination of rocky and icy material that evaporates as it warms when it's close to a star like the sun. But to start with, I'd like to address the rumors right at the beginning. I think it's important that we talk about that. This object is a comet. It looks and behaves like a comet and all evidence points to it being a comet. But this one came from outside the solar system, which makes it fascinating, exciting, and scientifically very important. This is only the third interstellar object like this that humanity has ever found. And a little bit more about the rumors. I think it's very important, and I'm actually very excited that a lot of the world was speculating about the comet while NASA was in a period where we couldn't speak about it due to the recent government shutdown. I think what I took away from that whole experience and watching that as we were working during the shutdown was just how interested and how excited people were about the possibility of what this comet could be. There was a lot of speculation about what it could be, but what I think is really awesome is that folks were interested in this incredible finding that we observed and that came from the heavens, and what that means, what it could mean about how magical the universe could be. It expanded people's brains to think about how magical the universe could be. And I'll tell you, here at NASA, we think that every day. And so it's really great that you were able to join us while we were, not able to comment because of the shutdown constraints about what that comet is, because we think the universe is a magical place, and we spend your treasure, and we spend all of our time trying to make sure that we explore that and share with you as much as we can. In fact, we want very much to find signs of life in the universe. In fact, just a few months ago, we were with you and we talked about what we think might be the signal from ancient life on the surface of Mars, from our amazing machines that have been roving the planet for 30 years to look for those things. That is something that's really important for us to learn about and discover. It could be an amazing discovery if and when we can confirm that. But 3i Atlas is a comet. So my colleagues from the Science Mission Directorate will go through the images in detail. But just to give you a peek, here's one of the images from the closest physical instrument we had to the comet, from the HiRISE instrument on our Mars Reconnaissance Orbiter, taken on October 2nd as the comet sailed by at a distance of 19 million miles from the instrument. You can see that Comet 3i Atlas looks like a fuzzy white ball. That ball is a cloud of dust and ice called the coma, which is shed by the comet as it continues its trajectory towards the sun. I'll leave it to my esteemed colleagues to share further details, and I'd like to introduce you to the head of NASA Science, Nikki Fox.
Thank you so much. It is such a rare opportunity for us to be able to observe this interstellar comet. And NASA Science has been given this really, really exciting opportunity to do it, and literally from the moment of its discovery. Just like Amit said, comets are tiny cosmic snowballs. And by studying them, we can learn about the environment from, basically where they formed, where they came from. This one came from a different environment from our own, and so we're already starting to see some really interesting differences to comets from our own solar system. 3i Atlas, as you heard, is the third known interstellar object to pass through our solar system, the first one being identified in 2017. While these types of interstellar objects have long been predicted, we are just beginning to be able to find them thanks to the newest technologies with our network of Earth-based telescopes, which are designed to find small, fast-moving objects in space. The NASA-funded Atlas Survey Telescope, which made the discovery, is part of NASA's Planetary Defense Network. Our telescopes are always watching the skies to keep us safe, and in doing so, they occasionally make major scientifically interesting discoveries, just like this one. Right away, of course, NASA's Planetary Defense Coordination Office they studied it, and they established that 3i Atlas is not a danger to Earth. In fact, it's at least twice as far away as the distance between the Earth and our Sun. On October 30th, the comet itself reached the closest it will ever be to the Sun when it crossed just inside Mars's orbit, which is why the image that Amit just showed, he noted it was the closest instrument physically to the comet, because the comet was right inside the orbit of Mars. Earth was on the opposite side of the Sun, which is about as far away as our planet can possibly be from Mars. It's been clear from the moment of discovery that the comet was going to pass on the opposite side of the Sun from where the Earth is. However, it was also clear that its positioning behind the Sun was going to make observations from Earth very, very difficult. And that is why we are so happy to have our incredible fleet of NASA science spacecraft all across the solar system. And boy, were they ready for this event. NASA's science assets on board our missions have provided the United States the unique capability to observe 3i Atlas almost the entire time it passes through our celestial neighborhood. Everything NASA science does is interconnected, and nearly 20 mission teams have been working together to really rise to this challenge. 20 mission teams, by the way, and counting. Everything we're learning about the comet is possible because of the distribution of all of the different instruments on our spacecraft with different capabilities. And I'll note that for some of them, we've even pushed our scientific instruments beyond their normal capabilities, beyond the things that they were designed to achieve to allow us to capture this amazing glimpse at this interstellar traveler. In other words, we can study this comet so well because we have many different assets in different locations, observing things in different wavelengths, in different ways, with different instruments, each set of observations providing a different lens for understanding objects in the sky. So NASA's science team has kept watch on 3i Atlas for nearly its entire journey through the solar system for the first time ever. So I'll just quickly go through the timeline of which NASA spacecraft have observed the comet thus far, and we're still going. There will be more opportunities to observe this comet as it continues its journey through the solar system, passing the orbit of Jupiter in spring of 2026. So the NASA assets that are gathering observations of 3I Atlas include Hubble, the James Webb Space Telescope, TESS, SWIFT, SphereX, Perseverance Mars Rover, Mars Reconnaissance Orbiter, MAVEN, Europa Clipper, Lucy, Psyche, personal favorite, Parker Solar Probe, Punch, Stereo, and ESA, NASA's SOHO mission. And I'll note that Parker Solar Probe's data were just downloaded yesterday, and indeed, we did catch several glimpses of this amazing comet. The scientific community is hard at work analyzing these images, and everyone, as always, is welcome to take a look. At NASA, we embrace open science. We make all of our data available to the public 24/7, and we invite, in fact, we really want you to tell us what you're observing and what you think about what we're looking at. We're still learning even about what questions we still need to ask, and this, of course, is the scientific process in action. All the data go to a public archive. We get those images as soon as we're able to from all of our eyes in space. As always, I am excited to see what new things we learn about our friendly solar system visitor in the days and, in fact, the years to come. So now I'm going to pass over to Sean. He's going to tell you about what our astrophysics missions have seen. They, of course, were some of the first things to look at the comet, and images from several of them have been available since the beginning of the summer. So I'm going to ask you to set the stage for us, tell us what we've already seen before we hand over to Tom to tell us all the new stuff. Take it away, Sean.
Thanks, Nikki. Happy to. To give you some background, NASA's astrophysics missions, like all our missions, they are designed to do things that would otherwise be impossible. In this case, our nation's space telescopes stare deeper and more sharply into the universe than any other observatories in the world. And that means we're often the first to follow up and study near-Earth objects or comets like 3I Atlas after they're initially detected. That same powerful gaze that lets these telescopes see distant galaxies, those little red dots you might hear about, they also allow us to observe details about objects like 3I Atlas a little bit sooner. And the earlier we learn about these objects, the earlier we can share this information with the world, including the science community and our partners across the planet that often have ground-based assets or other space-based assets, so that they can conduct additional observations with their telescopes. In this case, our astrophysics missions came together to take advantage of this rare opportunity to study this comet that came to us from outside the solar system. From our flagship space telescopes to smaller missions like TESS and SWIFT, they all have, as Nikki said, different complementary capabilities. They don't just do things that would otherwise be impossible, they do things that even our other great telescopes can't do. So every time we add to the fleet, we add additional capabilities that expand the realm of the possible. In this case, it let us refine the orbit of this structure early on, determine what its structure is and what its composition is, what it is made of. It's a beautiful illustration of why we have not just one space telescope, but a fleet of them, because every one member of that fleet specializes in a different kind of information, contributing a different piece of the puzzle to the total understanding we have from the fleet as a whole. So for example, Old Reliable, NASA's Hubble Space Telescope, celebrated its 35th birthday earlier this year. And not too long after that, in July, it looked at 3I Atlas, not long after we discovered it from the ground. At this point, 3I Atlas was about 277 million miles from Earth. And what Hubble's images revealed was a few things. First, a teardrop-shaped coma of dust coming off that solid, icy nucleus of the comet itself. From these data, astronomers were able to more accurately narrow a few things. Importantly, the size of the nucleus. We now know it's between, at that point actually, we knew it was between 1,400 feet in diameter up to as large as 3.5 miles in diameter. And Hubble also saw that the comet was losing dust, and not just losing it, but losing it at a rate consistent with other previous sun-bound comets that originated from within our solar system, consistent with the physics that we figured out from watching those objects. Now, the last thing Hubble did is it gave us a better understanding of the orbit of this object. Tell us not just where it was, but where it was heading, so we could point other observatories at it, such as the James Webb Space Telescope. We added this to our fleet early in this decade. We didn't have it when the last 2 interstellar comets came around. Now, what James Webb did, and its companion SPHERE-X, which we only launched at the beginning of this year, is it added infrared observations. The power of infrared observations is these are colors we can't see. They're redder than what our eyes can detect. And infrared light is particularly good at helping us understand the composition of objects. We can see little molecular fingerprints from the things that the objects are made of. So with these infrared observations, with James Webb and SPHERE-X, we detected an abundance of carbon dioxide gas in the comet's coma and in the bright cloud of gas and dust surrounding that comet as it approaches the sun. Those molecular fingerprints I mentioned, those are the little like science wiggles you might see in the top right of these images. We now know from seeing those science wiggles, those fingerprints of those molecules, that the comet has a nucleus rich in carbon dioxide as well as the presence of water ice. Now, the ratio, like we can not just say that these things are there, we can also say, what's the ratio of carbon dioxide to water? And we now know that. We know it's larger than what we usually see in solar system objects. But there's a lot of natural explanations for that. For one, the carbon dioxide is going to kind of bake off that comet earlier on when it's far away. But there's other well-understood processes that could also explain it. I'll just to put this in context. Every time we look beyond our solar system and we look at the ratios of carbon dioxide to water, we see, whether it's a star or a planet, different ratios than we see in the solar system, and that's true for this comet as well. So it could mean, and this is the last theory of why those ratios could be different, that these ices could have been exposed to higher levels of radiation than comets in our own system. Or, as I said before, could be that the comet just formed from a region where carbon dioxide ice was particularly abundant and different from our solar system. Other missions like our SWIFT spacecraft, which studies X-rays and gamma rays, have also observed the comet. Teams even looked back through data from our TESS mission, which was designed to look at exoplanets, and found observations of the comet as early as May. That information is helping us understand the comet's history before it got closer and when those other observatories pointed at it once we knew where it was. Now that the comet is near, relatively speaking, our planetary and heliophysics missions have joined in to tell us more. And now I'm going to turn it over to my colleague Tom Statler to talk about some of those new images.
All right, thanks very much, Sean. Before we get started, I just want to remind everybody of where we are, who is where in this play. As you saw in the animations while Nikki was speaking, the sun, of course, is at the center of our solar system. The planets are orbiting around the sun, and in this case, Comet 3I Atlas has come through on a trajectory in the opposite direction and has arrived at its closest point to the sun when the Earth was on the wrong side for us to conveniently observe. But Mars was on the correct side of the sun, and our Mars assets were able to observe the comet, and also several of our other spacecraft were on the correct side of the sun. So the scientific community is really excited about the comet and about these new observations. I'm tremendously excited to help share them with you today. This is a new scientific opportunity, and it's a new window into the makeups and histories of other solar systems. We're just beginning to learn about these types of objects and figure out what are the right questions we should ask about them. Now, let me start by going directly to what we were able to see at the beginning of September, when Psyche was able to see the mission. So before that, though, in August, we organized a workshop. We organized a coordination session for the missions across the NASA fleet that had good opportunities for potentially observing 3I Atlas so that we could all share observing plans and knew what was going to be possible with our assets. I can't emphasize enough now how, thanks to the cooperation of so many mission teams, we will be accumulating a wealth of data on this comet that the science community will be digging into for years. Now, let's go back to September, and I can show you a sampling of the images collected by our different mission teams. To set the context, you're going to see a comet that's a small body with a coma around it, basically a fuzzy blob. Now remember, space is big. Nothing is ever really as close as you like, and all of these observations are very, very difficult. It's a little bit as if our NASA spacecraft were at a baseball game, watching the game from different places in the stadium. Everybody's got a camera, and they're trying to get a picture of the ball, and nobody has a perfect view, and everybody has a different camera. Now, let's return to September and see the first images from the Psyche spacecraft. NASA's Psyche mission acquired 4 broadband black and white images of the comet over the course of 8 hours on September 8th and 9th, 2025. The comet was about 33 million miles from the spacecraft at that time, and you can see in the image the large frame where the comet was seen at different times. Down in the bottom left is a blow-up, a stack in addition of all of those observations. The Psyche spacecraft is on its way to an asteroid in the main asteroid belt that's also named Psyche, and these images were the first captured from this perspective. Now, if you think in that lower left you're not seeing very much, just wait a minute, you'll see more. Now, the following week in September, the Lucy spacecraft observed the comet from the opposite direction. So let's take a look at the Lucy image. This is another broadband black and white image made by adding up a series of individual exposures that were taken on September 16th. Lucy is on its way to study asteroids that share Jupiter's orbit around the Sun, called the Trojan asteroids. Lucy was 240 million miles away from 3I Atlas, which is circled in the center, when its high-resolution LaLaurie camera caught the comet. You can see the comet's coma, the fuzzy halo of gas and dust surrounding 3I Atlas, and its tail, a smudge extending to the right of the comet. If you were the Lucy spacecraft looking at the comet from this angle, the sun would be a little bit over your left shoulder, and so the comet tail is pointing away from the sun, as we've seen many times before in solar system comets. For scale, this image spans about 1/3 the width of the full moon as you'd see it on the sky. Of course, at the distance of the comet, that's a much, much larger region of space than the moon. Now, this looks a little different from the Psyche image. Part of that is because the cameras are different, and part is because of the ways the Psyche and the Lucy teams decided to show their images. But also, it's because we're seeing the comet from different directions. Seeing a comet's coma in different lighting geometries, with the sun coming from different directions, is one of the key ways to learn about the physical properties of the dust that's been launched off its surface. And I want to emphasize that you do not get these views unless you have spacecraft farther from the sun than the comet is, so that you can see it backlit. We could not get this view from the vantage point of the Earth. So combining the data from Lucy, Psyche, and Earth-based telescopes, scientists are hoping to better understand both the three-dimensional structure of the comet and the nature of the dust. It's a rare opportunity to compare ancient dust from a distant solar system to that from our own. Now let's go to the next picture from the MAVEN spacecraft at Mars. At the beginning of October, 3I Atlas passed within 20 million miles of Mars, which gave our Mars spacecraft an opportunity for a close-up. And earlier you saw the image that Ahmed shared from our Mars Reconnaissance Orbiter. MAVEN is another Mars orbiter that has been studying the Martian atmosphere since 2014. Now, this picture is not a direct picture of the comet itself. It's a spectrum. You're seeing the science wiggles that Sean was just talking about. This is some of those science wiggles where the instrument, the spectrograph, the ultraviolet spectrograph on MAVEN, has looked at the comet and also split up the ultraviolet light according to color. So you're seeing 3 different bands in this image. On the right, you're seeing emission from hydrogen gas in the atmosphere of Mars. In the middle, there's a fainter band indicating that's coming from hydrogen gas in interplanetary space. And on the left, that blob is the signature of hydrogen gas coming from comet 3I Atlas. It's a little blob rather than a big streak because the comet is a small object in the sky relative to great big gigantic Mars and interstellar space that fills the entire field of the instrument. That definitely tells us, first of all, that the comet is there. If there were no comet, there would be no little blob on the left side of the image. But it's also telling us it's one of the many ways that we're able to discern the chemical composition of 3I Atlas. And in this particular example, it's showing us the hydrogen gas that's coming off of the nucleus. Now, MAVEN's observations, combined with the earlier observations by Swift and Webb that Sean spoke about, will help determine the water production rate, how much water vapor is released from the comet when the comet is warmed by the sun, which provides insight into the formation of the comet and its journey through our galaxy. Now, the European Space Agency and NASA's Solar and Heliospheric Observatory, or SOHO, also successfully imaged the 3I Atlas from October 15th to 16th after it had passed Mars. And SOHO spotted the comet crossing its field of view from approximately 222 million miles away, or more than twice the distance of Earth from the Sun. Comet 3I Atlas was expected to be too faint for SOHO to see, but this result was made using detailed image processing and overlaying, or we call it stacking, subsequent telescope images. And this image highlights the value of spacecraft and instruments designed to look directly toward the sun, as Nikki was saying before, not only to study the sun, but also to have the ability to see other objects crossing, in this case, behind the sun from the telescope's point of view. You'll be able to see the rest of the images on our 3I Atlas website, go.nasa.gov/3i-atlas. And there will be more to come. Not all of the data have been downlinked yet through NASA's Deep Space Network, and there are more observations still in work. And also, it's a long way from where we are today, seeing the initial images, to then making sure that they are accurately calibrated and processed to do science with, and then doing the analysis, combining the data sets, understanding them, and finally producing the scientific understanding, the knowledge of what this all means, which will be published in peer-reviewed scientific journals. The answers will come later on. We are still at this phase, very much in the state where we're figuring out what are even the right questions to ask about interstellar objects. This is a snapshot of where we are very early in the scientific process. Okay, back to you, Courtney.
All right, thank you all for your opening remarks. We'll go ahead and start the question and answer portion of this event. Just a reminder to our media on the phone bridge to press *1 to enter the queue and ask your questions. We'll take our first question from the phone bridge from Marcia Dunn with the Associated Press.
Yes, hi. Based on your latest observations, what more can you tell us about the potential shape of the comet? Can you fine-tune any more on how big or small it might be, origin, all that sort of thing? Thank you.
Thanks for that question. There's a lot of territory to cover there, so let's see what I can do. The size of the nucleus still has yet to be pinned down. The best data are still from the Hubble observations that Sean was talking about. So we're still right now in that range of somewhere in the vicinity of a couple of thousand feet to a couple of miles diameter, but we'll get better on that one. The shape of the nucleus is also difficult to pin down because generally we're not resolving it in our observations. It's obscured by the dust, and especially it's obscured by the reflected sunlight off of the dust in the inner part of the coma. But what observers from the ground have been able to do is observe the brightness of the center of the comet over time to see if there's a modulation of that brightness that would be an indication of rotation. And it's very difficult to discern. So what it's looking like so far is that there's not a big, the shape of the nucleus is not very far from being round. Doesn't seem to be a big, or at least we're not seeing signatures of a very elongated object yet. There's a lot still to come there. I think you were also talking about origin. It would be great, it would be fabulous if we could trace back the incoming trajectory into the solar system and trace that back and figure out where it came from. But things are not quite so simple. Our galaxy, as Sean knows, is a big and complicated place. And the sun and all the other stars in our galaxy are in orbit around the center of the galaxy. And so 3I Atlas has been in interstellar space for a very long time. There is circumstantial evidence, given how fast it has come in to our solar system, that it came from some very old population, some solar system around a very old star. Quite possibly, we can't say this for sure, but the likelihood is it came from a solar system older than our own solar system itself, which gives me goosebumps to think about, frankly, because that means the 3I Atlas is not just a window into another solar system, it's a window into the deep past, and so deep in the past that it predates even the formation of our Earth and our Sun.
All right, we'll take our next question from the phone bridge from Bill Harwood with CBS. Bill, if you're talking, we can't hear you.
Try me again. This is Bill Harwood again. Can you hear me?
We have you loud and clear.
Okay, thanks. Sorry about that. I mentioned the rumors that were, kind of scurrying around about this thing in the weeks leading up to this briefing today. I have two questions for anybody who would care to answer. One is, did any of you seriously, did you take seriously the proposition from some that this could be an alien spacecraft? I doubt you did, but I'm asking the question anyway. And number two, is there any evidence you see in any of the data you have that would fit an explanation like that? Or as far as you're concerned, does all of this data say conclusively that this is simply a comet that happens to be passing through the solar system? Thanks.
So I'll take that one, Bill, and thanks for the question. We love all of the different science and all of the different kind of hypotheses into what these things can be. When you start seeing something, you just got to point. It's natural to wonder what it is. And we actually love, as Amit said, we love that the world wondered along with us. And that's such a cool thing. We certainly were able, because of the measurements that Sean described from the astrophysics telescopes that immediately turned on this object once we found it. And even, I was interested, I just learned that we'd actually gone back and actually seen it before we even found it. So that was super cool. I just heard that from Sean. But, we were very quickly able to look for sort of, the easiest thing to do, I'll put it in a different way, is if you understand comets pretty well and you understand asteroids pretty well, you kind of know the signatures that you're looking for, and so you can sort of look for those quickly and tick them off and say, yep, it really does behave like a comet. The interesting thing that, Tom, I know if I throw this to him in a second, he's going to geek out about it. But the really cool thing about this is the differences, because it comes from somewhere else. And that's why we're so excited about it. It's only the third time that we've been able to identify and track something coming from outside our own solar system. We've long predicted these things occur, and now, of course, we know better how to look for them, and we now have this amazing Atlas array. We're expecting we'll find a lot more of them, but it was quick. We were quick to be able to say, yep, it definitely behaves like a comet. We certainly haven't seen any techno-signatures or anything from it that would lead us to believe it was anything other than a comet. But the super cool thing is not that it's exactly like all the comets that we see in our solar system. It's the differences that are so tantalizing for us as it gives me goosebumps too. It could be from something that existed before our own solar system. That is so cool. It's from something that predates even our own star. Yep, it's going to look different because it didn't come from our solar system, and that's what makes it so magical. You want to geek out a little bit, Tom?
You were geeking out so expertly, Nikki, to begin with. So that was fabulous. But that's exactly right. I mean, things from other places, we naturally expect them to be different from our own homegrown variety. And I like to imagine if you're fortunate enough to have grown up in Hawaii and you only drank Kona coffee, you love your Kona coffee, and then somebody says to you, well, gee, have you tried Sumatran? You're going to say, well, do you expect it to be different? And they'll say, why don't you try this? And you try it and you say, wow, that's really different. And you realize, well, I expected this to be different because it was from someplace else. It was a different environment in Sumatra. Now, does that one sip of coffee tell you everything about the weather in Sumatra and the soil and the people who harvest the coffee. Bless them. Of course not, but it's different, and yet it's still coffee. And that's what we have in this case. We have a cometary body. It behaves, it resembles the homegrown comets that we have in our solar system, and yet it's excitingly different in particular ways. It does the same thing comets do. It evaporates carbon dioxide gas. It evaporates water. But it's evaporating more carbon dioxide compared to water. So that's a very interesting thing. Comets evaporate dust, and the dust is broken down. The minerals are broken down by the ultraviolet light of the sun. And comets, we know comets put out nickel, they put out iron. That's what comets do. This particular one is putting out more nickel than iron. That's really interesting, really remarkable, and something to be studied in the future. So we're always interested in new ideas. We're always interested in new suggestions, and all ideas are good when they're born. But those that stand the test of time, those that stand up to testing, those that are supported by the evidence, are the ones that survive.
All right, we'll take our next question on the phone bridge. And that one comes from Matthew Glasser with ABC.
Good afternoon. Thank you for doing this. Tom mentioned that the answers will come in time. I'm curious about what are some of the hopes that we might discover from this comet. What might it tell us about our planet, about our solar system, about the universe? Are there key things you're looking for as you start to analyze this data, and are you excited about anything in particular when it comes to better understanding how things are working out there?
Sure, I can take that. Every new object we discover is a new piece in the puzzle. What we're trying to do always is to understand the universe. That's part of the NASA mission, is to understand the solar system, understand the universe, understand the origin of planets, the origin of life. And that is a huge question, and we get little bits, little clues to parts of that puzzle, and we start trying to put that puzzle together. We have gained tremendous amount of information from hundreds of years of astronomical observation and from decades of in situ spacecraft observation has revealed our planets as actual places, not just points in the sky that you could barely see with your own eyes. We've learned about comets and asteroids, and we're beginning to put together a picture of how all of those planet-forming minerals and planet-forming ices came together to form our planets, and how our solar system changed over time. Just one example, we get a fascinating clue from the objects like Pluto that we've been discovering since the 1990s, the trans-Neptunian objects. The way they are distributed through space in the outer solar system show us clues to how the orbits of the major planets may have changed over time in the early solar system. A fascinating thing, and questions that we would never have thought to ask before we knew about these trans-Neptunian objects. Now, interstellar objects, like I said before, are new windows, and it's windows that we've never even looked out of before. So what we're going to find is way too early to predict, but I think we're getting a hint of the breadth, the wide spectrum of conditions that existed in different parts of the galaxy, in different solar systems, where the compositions, the elemental abundances, the mineral abundances may have been very, very different. It would be a different picture if we were seeing the first three interstellar objects and we'd say, gee, those look exactly like our homegrown comets. That would have been really interesting, and we would have said, well, maybe our galaxy is a boring place because every place is the same. What we're seeing with this is not every place is the same. That's a good thing. Lots of places to explore, and they will be different if we ever manage to get there.
Yeah, I think of these as frozen fossils from their moments of formation, including the things in and now from beyond our solar system. Or in some cases, we point our telescopes at other debris disks, which is just a whole system full of these small bodies. And so now what this will let us do is tell that story in a broader context between the detailed and large library of data we have on those origins of our own solar system, and how volatiles were delivered to make life possible here on Earth, combined with that big picture of other systems, of the dust spread throughout those other solar systems. And now with this visitor that got frozen in time from somewhere beyond our solar system, and that small picture of what that was like when that formed.
And the fact that, I love the sort of thought of it as that frozen fossil, almost frozen time capsule. we're kind of privileged. I mean, it's come into our solar system, our sun. We know, we think it hasn't seen a star for a long time. So it's actually warming up and giving us more information. It isn't just about a frozen object coming through and us sort of saying, oh, look, there's a frozen object moving through. But as it's almost waking up and showing us its composition, and that's allowing us to be able to do this great science. If it had just remained frozen all the time, we wouldn't know much about it. But it is the sort of its rendezvous with our star that is allowing us to really do this amazing science. And that to me is, it makes me feel almost privileged to actually be able to unlock the secrets as this cometary object is coming around and rendezvousing and interacting with our solar system.
All right, let's head over to social media. Nina on X asks, will it hit any planets in our solar system?
No, it will not. I think if you, obviously we're not going to run it again, but please, go online, take a look at go.nasa.gov/3i-atlas and take a look at the trajectory. I kind of talked through it briefly. Tom talked through it, and you can sort of see where those planets are. And remember this, even though it's exciting and it's coming through, space is huge, as both Sean and Tom talked about. And so the probability of it actually hitting anything is super, super small. You have to have all these things aligned to actually be able to do it. But certainly the objects in our solar system will be just fine.
And we have another question from social media from Astronomeum. They ask, what makes Comet 3I Atlas so different and intriguing compared to the other interstellar comets?
Tom, you want to take that?
The other interstellar objects. We say interstellar objects because not all of them were comets. So the first one was discovered in 2017. That was 1I Oumuamua that behaved very much like an asteroid. Again, a little bit like 3I Atlas, a very interesting asteroid, in some ways different from the asteroids we're accustomed to seeing in our solar system. For one thing, it was seemed to be very, very elongated, and while it was inactive, it seemed to be an inert, mostly rocky object. It did show indirect indications that it was evaporating gases in some way. It wasn't around long enough for us to get really, really comprehensive long-duration observations and understand exactly what it was doing. It was the very first one. We saw it for a short time when it was on its way out, in fact, and so we didn't get a great view of that. The second object, 2I Borisov, discovered in 2019, behaved, it was a comet. It was definitely a comet. It behaved in a lot of ways like our homegrown solar system comets, in many ways like 3I Atlas. Its properties were more in line with what we're used to seeing, and the comet observers regarded it as very much akin to our solar system comets, although in some ways a little bit at the edge of what we're used to seeing. 3I Atlas is in a lot of ways like 2I Borisov, but a bit more out there in terms of things like the carbon dioxide to water ratio.
All right, Svetlana on LinkedIn asks, will the observational data from this campaign be available for open analysis?
Absolutely. Every piece of NASA data, we are delighted to share. We've had open data policy at NASA for a long time. We make a big effort not just to release the data, but also to make sure it's usable, so you can get the tools and things to actually analyze the data as well. And we invite everybody to look at this comet with us. If you're able to take your own images through like citizen science programs, we love that too. We love everybody to be sharing in the joy of NASA science as we take every opportunity to take advantage of these incredible visitors to our solar system.
And that citizen science campaign, that includes work that citizens help us do to identify small bodies in our solar system. And so if you really want to get engaged beyond just looking at the data, you can help us generate new data and find other objects for us to study.
Yep, the big one, our solar, our SOHO, big comet finder, big comet tracker. So many of those comets discovered by our citizen scientists. So keep those observations coming.
All right, we'll head back over to the phone bridge. Our next question comes from Ken Chang with the New York Times.
Hi, thank you. This is for Tom and Nikki. One, of the measurements made so far, what is uniquely different about this comet, other than the trajectory, of course? And two, since perihelion, it looks like there are multiple jets. I was wondering if you could talk about that and the speculation that it might have exploded. Thank you.
Go ahead.
Yeah, thanks, Ken. So some of the differences I already mentioned is the ratio, the carbon dioxide to water ratio, the nickel to iron ratio. Also, there were ground-based observations noting that the polarization of the light reflected off the dust was also unusual, so that's telling us some interesting things about the dust. There are other indications that the physical properties of this dust, maybe the grain size distribution, might be different from the sorts of things that we're used to. The appearance of a sunward tail early on in the trajectory was part of that, an indication that the dust was being pushed off the comet on the sunward side, and then it took a while for the solar radiation pressure to push it back the other way. That's been seen before in other comets, but not very often. I'm sorry, Ken. What was the second part of the question?
The explosion.
Did it?
Perihelion.
Jets. Yeah. The jets. Right. So seeing more activity in the inner coma around the nucleus right around the time of perihelion, when it's being warmed most intensely, is something that happens frequently. That's something the comet observers are going to be very, very excited about. It does take some time to figure out, because it takes time for the actual event that happens on the surface to propagate out to a distance where you can see it with a telescope, but people are going to be mapping what jets there are. It doesn't necessarily mean there was an explosion. Jets can also just mean there are particularly active areas on the surface of the comet where more volatile stuff is evaporating in that one spot than elsewhere and jetting out. We saw this a decade ago with the ESA Rosetta mission at Comet 67P. It got up close and personal with the nucleus and saw frequently that there were jets coming out from specific places on the nucleus of the comet. So that could very well be what's going on here. Can't tell for sure, but that's the sort of thing we've seen before.
The other thing I just want to say that we're expecting to see as more stuff gets thrown off this comet in these jets is at those warmer temperatures, additional things can bake off of it, additional gases can bake off, and so we do expect the composition of the coma to potentially change, or those jets to change over time. And looking at the details of what other molecules we detect beyond the carbon dioxide and water we mentioned is also going to be interesting, especially for that sort of like, what was this stuff? What was the area in this? What was this stuff made of in the area it was made, like long time ago?
Right. Our next question is from David Chandler with Sky and Telescope.
Yes, a couple of things. Have you any of these observations showing you anything about any non-gravitational accelerations at this point? And also, can you say a little bit about coming attractions? What observations are in the pipeline that have been made but not released yet? I think the MRO high-rise observations, has that been released yet? And what else is there that's either in the can and waiting to come out, or observations that will be made over the coming weeks as the object comes closer to Earth?
Mm-hmm. I can answer some of that about the non-gravitational accelerations. This is something that we look very closely at for every comet, because that's always something that happens. And just to back up to explain what the question is that as comets evaporate, they are blowing off gas, they are blowing off dust, and every time something gets pushed off the comet, that acts like a little rocket engine at that moment and pushes in the other direction. And so it's very, very common to see comets have subtle changes in their orbits as a result of these little rocket forces, just called non-gravitational accelerations. So this is being monitored very closely. I spoke to our orbit determination team at the Jet Propulsion Laboratory earlier this week, and what they said is that this is being monitored. There are some changes to the orbit, but the uncertainties are still fairly large. It's difficult because we can't see the nucleus directly. It's difficult to get a very, very precise track on exactly where it's going. But so far, the non-gravitational accelerations have been very much on par with the sort that we see in solar system comets.
In terms of future observations, this is a situation where, because this is only the third time we've had an opportunity to look at an object like this, everyone that is in control of a telescope wants to look at it because it's a fascinating and rare opportunity. I know that our colleagues from the Keck Observatory have looked at it. I believe that we're going to look at it again with JWST in December. We have some other ground-based facilities that are giving us additional compositional information as those additional molecules bake off of 3I Atlas. Those are the things I'm aware of. There's probably a lot more that I'm not, because like I said, like every astronomer wants to get data on this thing because it's such a rare opportunity.
Yeah, and the high-rise image that you asked about specifically, Amit kind of rolled that out at the beginning. So please take a look at that image. I think Sean is not bragging a lot on what these astrophysics telescope. I don't know why, but because we are able to look at it in infrared with the James Webb Space Telescope, that will be the last time we can see the comet. So as it is exiting the solar system and getting further and further away, the James Webb Space Telescope will actually be able to track it longer than anyone else, partly because of its ability to kind of look long and deep rather than sort of across and wide, and the fact that it looks in the ultraviolet, in the infrared, so it can kind of see the dark objects. And so I'm really excited about just sort of, tracking it to the very end. Also noted, we're downlinking data from missions. I mentioned Parker Solar Probe because I just heard before we came on that we'd got some data and we'd seen the comet. I haven't had time to look at the data yet, but all of those things are coming up as we are getting more and more data coming down to us from those missions. And then as both Sean and Tom talked about, just really making sure we're sharpening up those images and really making sure they're calibrated. Right now we're putting out almost the raw images. We're putting out things quickly so everyone can see them, but we'll take some time and do some real sort of deep looking into those and do some more of the spectroscopy. Tom showed a really great example of kind of looking through the atmosphere of Mars, take out that hydrogen, take out the hydrogen from our solar system, and then let us look at the hydrogen that's coming from the comet. So we'll be doing a lot more of that as we move on to do great things with NASA science.
All right, that's a great lead into our next question on social media. Elijah on X asks, what kind of processing were the images subjected to and why did they need it?
You want to take that?
The images that were released received the sort of standard processing that we do between the raw data that comes down into a telescope. That, as Nikki said, we need to make sure for scientific accuracy that they're calibrated against the other observations, and we account for anything that the telescope is doing in that moment. And so that it would be our standard set of calibrations and normalizations for a object of this type, which is to say a comet.
I can add a little bit more to that. As Nikki said, our desire was to get these images out to the public as quickly as possible, and so there are some image artifacts in there that you'll see, and I can speak to the Lucy image that you saw previously. If you look at the comet, you'll see some blobs around the comet. Little blobs, faint blobs around the comet are not real. It came from the fact that in order to get this particular view, it was necessary, which is this backlit view, the team had to turn the spacecraft to face more toward the sun than it generally does. And so that means some part of the spacecraft were in the sun, and some of that bright, the sunlight reflected off parts of the spacecraft got into the camera, and that resulted in those little blobs. So that's an example of processing that has yet to be done to figure out exactly what that scattered light contribution was and remove that from the image so that what we show in the image is entirely what was there in the sky and not something just made by sun glints off the spacecraft hardware.
Yeah, and sometimes I think you showed the SOHO image where we actually stacked a couple of images, because a single image you wouldn't be able to see it would be too faint, but if we stack a couple of images together, then you can actually start to really make out what that comet looks like.
Okay, next, Gail on Facebook asks, how can an object like 3I Atlas come from so far, moving as fast as it is, and not hit anything?
Orbital dynamics and space is really, really huge. And so, you know, it is amazing to think about just how big even our solar system. And so to give you the Voyager spacecraft, Voyager 1, is now 1 light day away from Earth, which means when we send a command or we send a photon from Earth, it takes a full day for that photon to arrive at Voyager. And Voyager is only just outside kind of what we think of as the edge of our solar system. And so space is vast. Yes, this thing is moving quickly, and yes, it came from outside our solar system. But you know, the probability of it actually hitting something is so small, because everything has to align. It's also not quite in the ecliptic plane. It's not quite in like our normal. If you think about sort of looking side on at our solar system with the sun, and then you put the planets kind of in a row. Normally, everything sort of orbits in this plane. This is slightly tipped. Not unusual because it's not gravitationally bound to our sun, but it's slightly tipped. That makes the probability of it hitting it almost even greater.
If I can play with a scale model solar, if you make a scale model solar system where the sun and the Earth are 1 foot apart, that's about 1 foot. The sun is a P. The Earth, you need a magnifying glass to see, it's so small. The entire solar system will just barely fit in your house if you squeeze a little bit, and the next nearest star is over 50 miles away. So they call it space for a reason. Most of it is space.
Okay, we'll head back to our phone bridge. Our next question is from Brandon Spector with Live Science.
Hi, I wanted to ask about the age of the comet. You mentioned there's circumstantial evidence that it's much older than our solar system, but how can we constrain that age a little more? And what will that tell us if it is indeed much, much older than the solar system?
I can start that, but I'm going to pass it to Sean to talk about ages in the galaxy.
Okay.
So, cutting to the end, the bottom line is going to be, it's probably going to be really hard to get a more precise figure from one object. I think what we're looking at in the future, as we discover more of these, when we get to the point where we have maybe a few dozen of them and look at the distribution and properties, we may be able to get a better handle on what the distribution of ages is. So what's going on here is that it takes the sun 240 million years to orbit around the center of the galaxy, and we're doing that with a neighborhood of stars. So we're all going around the center of the galaxy. The relative motions between stars in our solar neighborhood is sort of 10-ish, 15, and sorry, I have all these numbers in my head in metric because that's the way I learned them, but 10 or 15-ish kilometers per second. So what is that? That's about 25,000 miles an hour, I think. And 3I Atlas is coming through at a speed of 60-something kilometers per second. So that's 3 times faster than the average of our local neighborhood, which is telling us that it's coming from a different population from what we have generally around us. Now, Sean will be able to clarify the age-dispersion relation in our galaxy, which tells us, which has been discovered over the last century studying stars in the galaxy, that the relative speeds of stars is an indicator of age. Stars that formed older in our galaxy over time increase their random motions for reasons that Sean will explain. And so that's the circumstantial evidence that makes us think that 3I Atlas came from a solar system that had larger motions relative to our solar neighborhood and is older. But it is a circumstantial and probabilistic argument.
So I'm just going to take this opportunity to brag about our telescopes and the James Webb Space Telescope in particular.
Go for it.
This blows my mind. We have data from galaxies closer to the origin of the universe than we have data from rocks closer to the origin of Earth, right? In other words, like if you pick up the oldest rock that we have from Earth, it is further away from the origin of Earth in terms of hundreds of millions of years than the amount of time there was between the origin of the universe and the earliest galaxies that JWST has now observed. And that's part of this story of how well we understand not just the history of our home planet, but the history of the entire universe that it's a part of. And now this is just another part of that story of the local neighborhood that our solar system is a part of.
All right, our last question for today comes from X and asks if we can see grains of sand on Mars. How is the clearest photo we can see for 3I Atlas what we've seen?
So because we're closer to the grains of sands on Mars, right? And so the JWST can only get like these single pixel blobs of the faintest galaxies, the furthest away galaxies in our universe. And because 3I Atlas is in our solar system, we can get the images and the compositional information with JWST. As it got closer to some of the planetary spacecraft Tom was talking about, they can't even see these galaxies, but because 3I Atlas was closer to them than they were to JW, they got really good images of the object as it passed by.
Right, as you said, we can image individual grains on Mars because we have spacecraft standing on Mars.
Right.
But even our closest spacecraft to 3I Atlas, we're still 19 million miles away.
And it's going too fast for us to send something there to intercept and get that close to it. So that's just not that we just don't have the. If we could. We would, we would be there up close and getting those grains.
All right, well, that's all the time we have for today. Thank you so much for joining us. Be sure to follow along with NASA as we continue to observe 3I Atlas. Find new images, detailed information, and resources by visiting go.nasa.gov/3I-Atlas and by following NASA Solar System on social media. Thanks for joining.
Pessoal, se você chegou até aqui, com certeza percebeu a riqueza do conteúdo científico desse material, né? É muito bacana, é um estudo muito legal sobre o 3I Atlas. E aí, vamos aproveitar para mandar aquele salve lá para o Alfredo, direto lá para Portugal, né? E outra coisa, se você quiser conhecer o trabalho do Alfredo é artista plástico, vocês sabiam disso? Na descrição desse vídeo aqui, tem o link para o portfólio do Alfredo, que é um trabalho incrível que ele desenvolve. Dá uma olhadinha lá, vai lá para vocês verem e comenta para mim. Você ainda acha que o 3I Atlas não é um cometa? Fala para mim aqui nos comentários que eu quero saber, ok? Bom, galera, se você curte astronomia, quer observar, quer comprar um telescópio, é no nosso parceiro, a loja Photon Astro, que é a maior loja de astronomia do Brasil. Lá na Photon Astro você vai encontrar binóculos, telescópios, oculares, filtros, adaptadores, tudo para astronomia, tá? E não é porque ela é a maior loja do Brasil que lá as coisas são mais caras, não. Pelo contrário, são mais baratas. Lá você vai encontrar os telescópios com maior custo-benefício no Brasil, tá certo? Então eu já deixei na descrição desse vídeo aqui o link, tanto para a loja Photon Astro, quanto para 4 telescópios que eu selecionei para quem quer comprar o seu primeiro telescópio para iniciar. Tá? Entrando por esses links aqui, vocês já vão comprar com desconto, né? Se você não entrou pelo link, você faz o seguinte, você usa aqui o nosso cupom, mas na dúvida pode usar o nosso cupom que está aparecendo na tela aí. Qualquer um pode usar lá direto, mesmo entrando no link. NERD aos 50, que aí você garante o desconto de parceria. Beleza, galera? Então é isso aí. Outra coisa, você curte muito o canal? Que tal ajudar esse conteúdo a chegar a mais pessoas aí? Ah, é fácil, sabe como é que você vai fazer? Senta o dedão no like, sentou o dedão no like, apareceu o botão hypar, senta o dedão no botão hypar, deixa o seu comentário, sua dúvida, sua sugestão, compartilha esse vídeo aqui para os seus amigos e inscrevam-se no canal. Quando vocês fazem isso aí, o YouTube entende a relevância do nosso trabalho e entrega ele a cada vez mais pessoas. Beleza, galera? Então é isso aí. Aguardo aí o seu like, o seu hype, o seu comentário, o seu compartilhamento e a sua inscrição para a gente explodir esse vídeo do YouTube afora e trazer mais espaçonautas para cá. Grande abraço, até o nosso próximo vídeo.